So just a quick recap of grade 10 electrostatics. In grade 10, you learned what happens when objects touch. So if two objects are charged, or one is charged and one is neutral, what happens when they touch if they are conducting materials? Your charge will always even out. So the charge together of both objects, you add that together and divide it by the two objects. If there are three objects touching, you take all the charge of the three objects, add it all together and divide it by 3. So that after objects touch, they all have the exact same charge, the same magnitude, and the same type of charge. So if the overall net charge is negative and you divide that by 3 or by 2, then each will have negative charge as well. Okay, so that means that when objects touch, because they become charged exactly the same sign as well, they will always repel after they touch. So they might attract and then repel. Okay, that repulsion that we get is because they become charged with the same amount and the same type of charge. Okay, giving us a repulsive force. Now, we can use this first equation over here to tell us how much charge is on each object after they touch. But this one down at the bottom, we use to say how many electrons move over from one object to another, because electrons are charge carriers. Okay, remember each electron carries an amount of charge of 1.6 times 10 to the negative 19 coulombs. It's negative charge, and protons will carry a positive amount of charge, same magnitude. So when electrons move over from one object to another, they move 1.6 times 10 to the negative 19 coulombs of charge per electron. Okay, we say that charge is quantized in that value. In other words, you can only move whole electrons around. So you can only move packets of charge of 1.6 times 10 to the minus 19 coulombs. You can't move a portion of that charge around. Only whole electrons can move. So now you want to know how many electrons have moved across. So if you have two objects, let's say we have two objects, we have a 5 coulomb and a let's say a negative 1 coulomb. Okay, now they touch. So after they touch, we add the charge together. So we go 5 plus a negative 1, and we divide it by each object, giving us afterwards on each object, what's that? 4 divided by 2, so 2 coulombs of charge on each. So they both get that positive 2 coulombs. But now how many electrons have moved over? Well, we first need to figure out how much charge is moved over. Remember, charge will always move from the object that is more negative to the object that is less negative. Why? Because we are moving electrons. We are moving negative charge. So where there is more negative charge, that will lose electrons to the object that is less negative. So the charge is going to move from the 1 coulomb to the 5 coulomb. How much charge moves? Look at the difference between what it was and what it is. It was 5 coulombs. It is now 2 coulombs. That means negative 3 coulombs has moved across. Okay, for both. What's the difference between minus 1 and positive 2? The difference is 3. It has to be negative because you're moving electrons. So you look at the difference between 5 and 2, the difference is 3, and it's a negative 3. The difference between minus 1 and 2, the difference is 3, but it's a negative 3. Everybody okay with that? So that tells us how much charge has moved over. It is always negative charge because we can only ever move electrons. Now, how many electrons have moved across? Well, we're going to take the charge that's moved across, so that's the minus 3 coulombs. So we can put minus 3 coulombs there and divide that by the charge on an electron, 1.6 times 10 to the minus 19. That gives you the number of electrons that has moved across. So all the charge in total that's moved over divided by the charge per electron gives you how many electrons move across. Now you can either substitute in both of these as negative, or you can substitute both in as positive. It really doesn't matter. In electrostatics, we tend to leave off the negatives when we substitute in, just because directions are reasoned most of the time anyway. Okay, so whatever you decide to do here, just make sure it's a positive answer, because you can't move a negative number of electrons. Okay, they whole objects, they're whole little particles, so we can only move positive number of electrons. So just make sure your answer is positive and you're fine. That was a lot of information. You guys okay with that? That is the recap of everything from grade 10. Okay. You need to know your conversions off by heart. Okay, so how do you convert? If you've got something in microcoulombs, you swap the micro for the times 10 to the minus 6. So if you have 3.42 microcoulombs, you will swap that and you'll go 3.42 times 10 to the negative 6 coulombs. Okay, so you're swapping the micro for the times 10 to the negative 6. You just swap it over. The number stays the same. So very easy conversions, as long as you remember to study this table. If you don't, trouble. You must always substitute in values in coulombs. Okay, make sure you're always converting back to coulombs. So Coulomb's law. The difference between IB and DBE is not very big. It's only the first little bit. The basic point here is the first part of this definition describes what kind of force we're defining. So it is an electrostatic force between charges. The DBE describes it as the charges, the electrostatic force exerted by one charge and another. And the IAB says that 2 point charges in a free space or air will exert a force on each other. So you're just describing what kind of force it is. The second half of this definition, we're going to use our formula to remember, because it's very wordy, and to remember that off by heart without anchoring it to something tangible is difficult. So you have your formula page with you in your exam. Use your formula page to remember your definitions. Okay, so we've described this force. Now we say the force is directly proportional to the product of the two charges. How do we know that? Well, they multiply together, so it's the product of the charges. Our force is above the line, and our charges are above the line. So if they're both above the line, they are directly proportional. And inversely proportional to the square of the distance between them. So our force is above the line, and our square of our distance is below the line. So if you've got above the line and below the line, then they are inversely proportional. Okay, so the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Use your formula to remember your definitions. You should actually be studying your definitions with your formula page in front of you, and then be able to point to a formula and say the definition as you point to the formula. If you can do that, you're going to save yourself a lot of hard work. Okay, it makes it much easier. All right, when we sub in, make sure that your charges are subbed in coulombs, your distance always in meters. Now here, they're small spaces normally with electrostatics, so you're going to be looking at millimeters and centimeters. Make sure to convert them to meters, and then your force is still in newtons. Okay, K has a value of 9 times 10 to the positive 9. All right, that value is on your formula page. So we have two types of sums in this chapter. The one kind of sum is just a plug in and calculate the answer, and the other kind of sum is the ratio sum. So for the ratio sums, this, you'll know it's a ratio sum when something has changed. Either you have charges moved to a new distance, or the magnitude of the charges is doubled, or maybe the force is even halved, but you're looking at a scenario where there's a change to the scenario. As soon as you see that, think about ratios. You always often use it if you don't actually have information to plug in. So they haven't told you how big the charge is, but they've said the charge doubles. That should trigger, okay, wait, I'm doing a ratio sum. Now, there are easy ways to think about the ratio sums, and that's great if you're doing multiple choice questions and you know how to get to the answer very quickly. So if you know how to shortcut this, that's great, but you must also know how to write this out. and show the working for the ratio problems. If you don't write the working out properly, then you can lose significant marks for that. So how does the working go? We've got two charges experience a force F, that's our original charge. And now they say, how would the force change if one charge is doubled and another is tripled and the distance is halved? So three changes here. Your original force F has got the original formula. The new force, label it differently. So label the first force F and then the new force, so that you can see that there's a difference between the two. Okay, so the new force, one of the charges is doubled, the other one is tripled, and the distance is halved. Any change to the distance must be put in a bracket so that you can square the change. Otherwise, you're not going to square that half. Now we need to clean up our formula. We need to try and get our formula looking like the original. So we pull those values out again. 2 times 3 gives us 6. A half squared gives us a quarter. 6 divided by a quarter gives us 24. And this is our original formula, which represents the original force. Okay, so our new force is 24 times the original force. Practice writing it out like that. So the biggest thing is that you must be able to distinguish between the original force formula and the new force formula. Okay, if you do that, you should be fine. Okay, Betsford, do you have a question? I see unmuted.
Oh, sorry, no, ma'am.
Okay, no problem. The table, so the difference between big Q and small q. Big Q and small q is the same thing as saying Q1 and Q2. So it's just a way to distinguish between two different charges. It's one of the very few physical quantities that have both the capital and small letter assigned to its physical quantity as a symbol. So it's the same as saying Q1 and Q2, big Q and small q. You're distinguishing between two different charges. Where it does come in handy is when we get to the fields. So I'll talk a bit more when we get to the fields, because they use the different ones in the different formula. Okay, so I'll talk about it a bit more now. Right, guys, then when we're substituting in because the electrostatics vector nature doesn't work the same as our forces vectors, where we've got everything to the right is positive and everything to the left is negative. So therefore, if we get a negative answer, we know it's in which direction. It doesn't quite work that way. The positive and negative here tell us what kind of charge there is, and that tells us if our field is going to radiate outwards, or if our field is going to radiate inwards, or if our two charges are going to attract, or if our two charges are going to repel. So the direction of the force and the direction of the field still needs an extra step of reasoning. You have to think about it a little bit. So you can't just go, okay, well, this one's negative and that one's positive, so this one must be left and that one must be right. You've got to think about it, okay? And because of that, we can leave negatives off of our substitution. So only substitute in positive charges. Don't substitute in negative charges. You just leave the negative off. If you put the negative in, that's fine. Okay, you can put the negative in. You have to reason the direction anyway. Okay, so it's your choice whether you want to substitute in a negative charge or just substitute in the magnitude and leave the negative off. It is up to you, but I'll show you how to reason these directions. Okay, so this is one where we have to find the resultant force on QB. Now, there's three charges here. There's a resultant force on each charge. Each charge is experiencing a force from the other two charges. So you can calculate the resultant on A, you can calculate the resultant on B, and you can calculate the resultant on C. Our question is asked for B. Okay, now, the easiest way to get to the direction is to draw a free body diagram. Guys, you will never escape free body diagrams. Use it in every single chapter that you do. Okay, so they want the force on B. So this is B, the free body diagram of B. Look at what B is going to do. A and B are going to attract each other. How do we know that? A is negative, B is positive, opposite charges attract. So A will be attracted towards the right and B will be attracted towards the left. So B experiences a force towards A, towards the left. Now B is also attracted towards C, okay, because B is positive, C is negative, they attract each other. C will be attracted towards the left, B will be attracted towards the right. We're interested in what B is doing. So B experiences a force from C towards the right. Now we've got the directions, okay? So because those two directions are opposite, we're going to subtract our forces from each other. Your free body diagram will help you with this. So now we plug in everything. Make sure that you're converting your nanocoulombs to coulombs by adding the times 10 to the minus 9. Make sure that you are converting your centimeters to meters by adding the times 10 to the minus 2. Don't forget to square your distance. And then when you get your two answers right in the values, so the force of A on B is to the left and the force of C on B is to the right. If you put your directions in at this point, it does help you to go further. The one's to the left, the other one's to the right. So we subtract the two and it's in the bigger one's direction. So your resultant force is to the left. So when you're looking at direction of force, look at the movement. I'll put that as a note. Oh wait, I mean not right here because the recording puts the video in there. Direction of force. Look at the movement. Okay, so you're looking in which direction your charge is moving to. Okay, so Priyanka, how would you determine the direction if they ask for the resultant on A? Okay, let's see what A is doing. So if we're focusing on A, we draw a free body diagram of A. A is attracted towards B, so it experiences an attractive force towards B. So B will pull it towards the right. But A and C are both negative charges, so they will repel each other. So A will be pushed towards the left because of C. So it will experience a force towards the left because of C. So you will still subtract the two from each other, but for different reasons. Okay, does that make sense? Cool, good. All right, guys, let's have a look quickly at a two-dimensional one. So this is one-dimensional, so we look just working left, right. Now, a two-dimensional one is where we have a 90-degree angle. So again, you're going to look at the free body diagram. So determine the resultant electrostatic force on B. What's B going to do? B is negative. C is positive, so B is pulled towards C. It experiences a force in that direction. B is negative, A is positive, so it's pulled downwards towards A. So it experiences a force downwards. The resultant force is therefore going to be in that direction. Okay. Your free body diagram will help you. So now you just go and calculate the two. So we know the force of A on B is downwards and the force of C on B is to the right. And we use Pythag then to get the resultant. So you can maneuver these into a triangle by taking your FA and putting it on the other side so that you get your nice triangle. You use Pythag to get the magnitude of the resultant and then the direction. Guys, you need to be so careful with these directions. This is going straight back to vector sums that you did with Newton's laws. And these vector sums, I think we're recapping them quickly tomorrow morning as well. I'm with you guys again tomorrow morning for vectors and Newton's laws. But this is straightforward vector stuff. We can't say southeast for two reasons. First of all, they didn't give us southeast to use. You can only use your coordinates, your northeast, south, and west if it's stated in the question. Okay. And then southeast is a very specific direction. It's exactly 45 degrees, which this is not. So you have to calculate an angle to get the direction. So we're calculating our theta over here. So you can use your opposites over adjacent. You can use sine, cos, or tan. You've got all three sides. Okay, so a little bit of trig, and we get the value of theta. Reference your angle, because maybe you chose alpha, maybe you chose a different angle. Okay, you have to say where you measured your angle from. So you can, it doesn't matter which angle you calculate, you have to reference it. So you've got to say it's below the positive x-axis or clockwise from the positive x-axis, as long as you say where you've measured it from. Latabo, did I answer your question? Sorry, I just saw it in the chat now. How do you know where theta must be? You choose. Okay, so you can literally choose any angle, but just reference it. Okay, I saw a hand pop up. Did I miss something? Is anybody want to ask a question? Yes, Priyanka.
Sorry, ma'am. I just want to find out, in our mid-year exam, in the example on the left, for B, they hadn't given us the charge and they asked us to determine whether the charge was positive or negative. And
Okay.
I just had no idea what to do. So what would you do?
I don't know the context of the question. Did they give you the resultant force?
No, it was exactly like this, but I can't remember the directions of the arrows. It wasn't up and down. It was only one direction of the arrow.
Oh, okay. So then I'm guessing here because I don't know what it looks like, but maybe did they draw a field diagram? So did they so an electric field, so maybe something like that.
Yes.
Okay, so your negative fields come inwards. The direction of a negative field is inwards. The direction of a positive field is outwards. So with the field arrows showing inwards, it probably, if those were field arrows that they were drawing, then that would indicate that B would be negative.
Okay, that makes sense. Thank you, ma'am.
Cool. Okay, let's move on. So now we get to the electric fields. Okay, so this is where our directions become a little bit interesting. Okay, so we're going to look very carefully at the directions here. It works a little bit differently. Remember, forces, you look at the movement. The fields, you look at the pattern. You got to know your field patterns. Okay, when you read your questions, guys, I don't know if you read with a highlighter or if you underline words with your pen, but electrostatic force and electrostatic field look very similar and they are often misread. So when you read that, I want you to highlight fields and force. I want you to highlight it and I want you to think about it before you carry on reading the question. Be very careful what you are calculating. Fields is your E, okay? Force is F, fields is E. Okay, now an electric field. So it's described as the region in space where a charge experiences a force. So what is an electric field? It's just space. It's just nothing. Okay, there's no lines. There's nothing running from the one charge to the other charge. It's empty space. That's what a field is. But what's special about the space? If you put a charge into it, the charge will start to move. The charge will start to experience a force. Okay, our gravitational field is very similar. So with our gravitational field, that is just a space around the Earth, especially around any object with mass. But the Earth is big enough for us to experience it. If we take a particle with mass and we put it in this gravitational field, it's going to experience a force. That's how we know it's in a gravitational field. If I put this pen here and I left it and it just hovered, it wouldn't be in a gravitational field. Now that's the same thing as an electric field, except an electric field is a charge. So if I take a little charge and I put it down and it doesn't move, I haven't put it in a field. But if I put the charge down and it moves, I've put it in an electric field. Okay. Now, the direction of that field is determined by the direction that a positive charge will move in. Remember, there's nothing running or moving from one charge to the other. Our field lines are there as a kind of an understanding for us. Asante, do you have a question? I see you unmuted.
No, sir, ma'am.
Okay, no problem. All right, so If I put a little positive charge down here, what's going to happen? It's going to be repelled by this positive charge. So 2 positive charges repel. And that's why the field pattern around a positive charge radiates outwards. It's pointing in the direction that a positive charge would move in. If I put a positive charge down over here, it's going to be attracted towards that charge because positive and negatives attract. So the field around a negative charge radiates inwards to show this is the direction a positive charge moves in. Obviously, guys, a negative charge does exactly the opposite. Okay, think about that carefully. The force direction is the direction the charges move in. But the field direction is the direction a positive charge moves in. It's like a decision that was made and everybody agreed on it and they were happy about it and they decided that is the direction of an electric field. Not because something moves in that direction other than a positive charge. Got it? So that's why it's away from positive towards negative. So the unlike charges, opposite charges, they attract. So you get a resultant field in the middle. In other words, the field in the middle of these 2 charges is both in the same direction. And because they're both in the same direction, we add those fields together and get a resultant field at that point. If we're looking at like charges, the field direction in the middle is in opposite directions. So we would subtract the 2 fields in the middle to get the resultant. And if it's right in the middle of 2 identical charges, those 2 fields cancel out and give us a resultant field of 0. That's what this little space is for. This little space here shows us that somewhere between these 2 charges, there is a resultant field of 0. Okay, and the same with the 2 positive charges. When you guys draw these, you must be careful with the number of field lines for different magnitudes of charge. The number of field lines indicate which charge is a greater magnitude and a smaller magnitude. Okay, I'll show you an example of it now. Quickly draw one on the next slide. I think there's some space. So the resultant field somewhere in the middle of 2 like charges, there will be a resultant field of 0. Okay, now if I can just illustrate that here quickly, these are also just diagrams that you need to be able to draw. Okay, now if I can just illustrate that quickly, let's say we have a 5 coulomb charge and a negative, so let's say negative 5 coulomb charge and a negative, I don't know, 8 coulomb charge. The negative doesn't mean anything other than the direction. Okay, so something's not a greater charge because it's positive and the smaller charge is negative. You look at the number to see which charge is greater. So a positive 5 will be smaller than a negative 8. The positive and the negative is just the direction. Got it? So if we're trying to draw the field, the resultant field between these 2, they are going to repel each other, but the negative 8 coulomb charge is a greater charge. It needs more field lines. But it also means that its field is a little stronger. So when it exerts, oh, that's a bit 90 degree, but anyway, I should make a smoother curve than that. This pen is not the easiest to draw with. Oh goodness, I've lost my thing here. Okay, what I've done here is because the negative 8 is a stronger charge, its field is stronger further away. It has a further reaching effect. So the point where they cancel out is going to be closer to the smaller charge. It's not going to be right in the middle. It's only right in the middle if you've got the same size charges. But if the charges are different sizes, the bigger charge has a further reaching effect. So you always draw that little net 0 point closer to the smaller of the 2 charges. Okay. Now, when you draw your field lines around this one's going to have fewer field lines, and this one's going to have more field lines. Please don't go to your teacher and say, but count them. There's more lines. The teacher's not going to count them, right? It's got to be obvious. Let me just erase my little circle here in the middle. There we go. It's got to be obvious, guys. Okay. So obviously more lines around the greater charge, and then move that little net 0 point closer to the smaller of the two charges. Any questions there? Obviously you need your directions, hey? And this is negative, so it goes in towards the charges for both of them. Oopsie, towards. All right. Everyone happy with that? Good. I'm taking your silence as a good thing. Not that you're sleeping. Okay. Electric field strength. Remember, we described an electric field as this region in space where a charge experiences a force, but the strength of that field is described by the amount of force experienced by 1 coulomb of charge, per coulomb of charge. Now, this formula here is your definition formula for the electric field strength. In other words, use your formula page and write on there definition for electric field strength. What are we doing? The amount of force experienced per 1 coulomb of charge. Okay, now we get to this idea of big Q and small q. Remember, I said big Q and small q are only there to distinguish between two different charges. But when we talk about our field strength, we actually use the two in two different formulae. Now, both of these formulae say the electric field, talk about an electric field. You're working out the magnitude of an electric field. Both of these values is this charge's field. Big Q's field. So what do you have? You've got a charge and another charge. Why do I make this one big Q? Because I'm working out that one's field. The small q just experiences that field. Small q has just been placed in that charge's field, but I'm calculating big Q's field. If I want to calculate the other one's field, then that becomes big Q. Does that make sense? I assign the capital Q to whichever charge whose field I am calculating. All right? So if I use this first formula, I'm using another charge to calculate this one's field. I'm using the charge in its field to calculate its field. I'm still calculating big Q's field. I'm not calculating small q's field, but I'm using another charge. I'm using small q to calculate this one's field. Okay. If I use this formula, then I'm using my big Q and I'm saying how far away am I from it and what's its magnitude. So how strong is this charge? What's my distance away from it? And that's going to help me calculate its field at that point. So how do you know which formula to use? Go with what information has been given. If they give you a force, look for a small q. If they give you a distance, look for a big Q. Okay. So if we look at the example here quickly, I just want to show you the wording in this example. Here, charge A experiences a force of 2 newtons due to charge B. Now, the way this has been worded is a little bit tricky because keep in mind, both charges experience the exact same force. Why? It's a Newton's third law force pair. So if A exerts a force of 2 newtons on B, B exerts a force of 2 newtons on A. There is only one force between the two. You use both charges to calculate that force, but both of them experience the exact same force in two different directions. So if A experiences a force of 2 newtons due to B, then B experiences a force of 2 newtons due to A. Okay. Now the next bit of wording is the tricky part. Determine the electric field strength at point B. I'm looking for the field strength here. Which charge is big Q? It has to be A. It can't be B. Why? Because if I use this calculation, okay, if I use this calculation and B is big Q, what's my distance from B at point B? My distance is 0. You see that? If I'm calculating B's field at B's position, my distance is 0, which is undefined. I can't put it in that formula. So I can never calculate this charge's field at that point where that charge is. I can only calculate this charge's field a certain distance away from it. Think about that carefully. Okay, I can only calculate this charge's field a certain distance away from it, not at its point. So if I'm looking for the field strength at this point, at this position, I'm looking for A's field. So A is the field who I'm working out. B is the charge who's in that one's field. So B just becomes small q. And now there is a typo over here. So we're going to take our force experienced per Coulomb charge. Our B is small q. The force is 2 newtons. We're going to put 5 over here. And that's going to give us 4 times 10. I think this is also a 5 times 10 to the power of 5. So there was a typo here. Just fix that in your notes. Okay, so B is small q because I'm calculating the field strength at that position, which means B is experiencing the field of A, and I'm calculating A's field. But the question gave me something about force, which should make you automatically think to use that formula. If the question says something about the distance, so here the question has given you big Q is 3 microcoulombs, and they've given you a distance away from it and a position P. There's nothing at P, it's just a position. There doesn't have to be something at P. There is still a field strength there, okay? There's just no force because there's no second charge. But at this position, I can calculate Q's strength. Q is big Q because it's the only charge there to calculate. But now I'm using the distance away from it. So I'm using the other formula. So look at the information that's been given, and that should help you to decide which formula to use. Okay. Let's quickly look at the directions. I'm just going to go back quickly. This one's direction says to the right. Now, why? A is a positive charge. You have to look at the pattern around that positive charge and look where you are around that positive charge to decide what the direction of the field is. Now, if I draw in the field here for A, okay, it goes outwards because it is positive. Now, B is sitting directly to the right of A. Now, if I look at from this point of view, if I'm looking from here, this is the field direction. A is pointing to the right, and that's why my answer is to the right. If B was sitting on the other side of A, then my direction would be to the left. Okay, so for field direction, look at the pattern. Pattern. Okay, so you're looking at the field pattern around the charge, and you're deciding where you are around the charge. From that point of view, what direction is that field pointing in? If we look at the other one's direction, so this one also is to the right. It's also a positive charge. Okay, so if you're looking from this perspective, you're looking at that arrow. Okay. If you're looking from this perspective, you're looking to your arrow is pointing to the left. Check quickly. Are you guys happy with that? No questions? Okay. Right, that is it. So just remember, the electric field is also a vector, so you can add them together the exact same way as you do the forces. Your free body diagram will help you here as well. So let me just clear this writing quickly, and I can just show you something quickly here. If we had to look for a net field at this point over here, you would look at the field pattern for A. You would calculate A's field. So you'd say, okay, from this point, A's field is pointing to the right. So if I draw a free body diagram of that, A would give you a field to the right. B is a negative field, so the field radiates inwards. So if I look from this perspective, I'm looking at an arrow also pointing to the right. So there are two fields to the right, which means I would add those two fields together to get the resultant field in the middle. Okay, so you look at the pattern, you look at where you are around that pattern, that gives you the direction of the field. You guys happy with that?
Yes, ma'am.
Cool, awesome. Okay, so that brings us then to the end of the theory. We are going to look at question number 3.1. So for 3.1, we've got 3 small identical metal spheres, P, S, and T, on insulated stands. They are initially neutral. I'm just going to try and enlarge this slightly. Hang on, this thing is very sensitive. Oh, so sensitive. There we go. Okay. They are then charged to carry charges of -15 times 10 to the minus 9 coulombs. That would be a nanocoulomb. Q, and 2 times 10 to the minus 9 coulombs, respectively, as shown below. So the charged spheres are brought together so that all 3 spheres touch each other, and then they are separated. The charge in each sphere after separation is -3 nanocoulombs. So the one to know, determine the charge on Q. Okay, so all 3 of them are brought together before the time. So your charge after they touch is equal to -3 times 10 to the minus 9. How do we get that? We add them all together. So we've got 15 times 10 to the minus 9. I'll just move this page up a little. Okay, plus Q plus 2 times 10 to the minus 9. And we divided that all by 3. Okay, so they all touch. Afterwards, they each have a charge of -3 nanocoulombs. So we're looking for Q, we just solve for Q, and then we get Q is equal to 4 times 10 to the minus 9 coulombs, or 4 nanocoulombs. All right, so just that. When they touch, the charge divides equally. Draw the electric field pattern associated with the charged spheres S and T after they are separated and return to their original positions. When they've separated, they each have a charge of -3 nanocoulombs. So they have the same amount of charge, and they are both negatively charged. So they will repel afterwards. So you'll have 2 negative charges, equal magnitude, which means that your little net zero spot is going to be in the middle. Ooh, it's bad. And then you're going to draw field lines around here, and you're going to try and get the number of field lines equal. Please remember your field line rules. They are not allowed to touch each other. They'll have the same. They're not allowed to touch each other. They're not allowed to start off of the charge. They must start on the surface of the charge. Kind of try and get the 90 degrees. I'm missing 1 line on the left. I see that. And then make sure that you've got your directions in. Okay. Practice drawing these, guys. If you get a nice way to draw them, then you'll know that you get this right in the exam. But they are finicky to draw, so practicing them is not a bad idea. Try and get a method for drawing these things. Okay, don't just wing it. Because if you're going to wing it, it's going to end up wrong. Then if your lines touch each other, by the way, you lose marks, eh? Okay. Our next one says state Coulomb's law in words. So I'm not going to go through that. That's just a definition. Your definitions, by the way, guys, if you are, you know yourself. If you have a habit of losing marks on definitions, then just by knowing your definitions, just by making that one change, you can increase your mark by an entire symbol. So if you normally get a B, but you get your definitions wrong, you can get an A. If you normally get a C and you get your definitions wrong, you can get a B. It's a very quick fix, hey? So really worthwhile putting the effort in to learn them word for word. So the spheres, each with a new charge of 3 nanocoulombs or -3 nanocoulombs, are now placed at points on the X and Y axis, as shown in the diagram below. Again, state Coulomb's law. Calculate the magnitude of the net electrostatic force acting on sphere P. Now, first of all, the magnitude. We don't need a direction here, okay? Just the magnitude. We want the net electrostatic force acting on sphere P. So that one over there. So start off with your free body diagram. Look at what it's going to do. They are all negatively charged. Okay, remember they all carry a charge of -3 nanocoulombs. So P will be repelled downwards because of S. So it experiences a force downwards because of S. And it will be repelled towards the left because of T. So those are your two forces giving you a resultant force in that direction. Okay. Now we just need to go and calculate the magnitude of these two forces. So if we go the force of S, so we've got force of S, we've got K, we've got Q, P, Q, S over R squared. Don't get confused with force and field. Remember, this is a force, so we're looking for F. Okay, so K is 9 times 10 to the 9. QP, well, both of them is -3 times 10 to the -9. So you can put that in twice or just square it. They both have the same charge. And then our distance is 0.1 meters. So it's already in meters, but don't forget to square that value. And that gives you 8.1 times 10 to the -6 newtons down. Okay.
Ma'am?
Then, yes.
Hi, ma'am. With the free body diagram, right? The net force is in between like the FT and FS, right? So like when we get theta, we can put theta anyway on the
Yes, you
diagram.
can. You can either put it over there or you can put it over there. It really doesn't matter. You're going to reference that anyway.
Okay, thanks, ma'am.
Okay, cool. Just remember that would be if they didn't ask for magnitude, hey? So we're not going to do it for this one because this one just wants the magnitude. So we don't have to calculate the direction.
All right.
Cool. Oh, okay. Rotendo, so the sign, adding in the negative. Okay, I've substituted in the negative. It is entirely up to you. You can substitute it in, or you can leave it off. They've actually made provision to leave it off for the electrostatics just because it ends up making people confused. You want a positive answer and you want to reason that direction. You don't want to just take everything negative as left and everything right is what did I say? Everything positive is right. So you don't want to just you have to reason that direction anyway. That's why they've made provision to leave it off. So it's more of an option to put it in, but you don't have to put it in. Okay. Oh, Jajelo, so the distance, let me quickly just check here quickly where we, so the distance over here, that was given over here, there. So between P and S, they said that the distance there was 0.1 meters. See it? And then the other one's distance that we're going to use is 0.3 meters. So we actually just got that information off the diagram. Guys, they are moving more towards that, hey? So putting more information in diagrams and less information in paragraphs in the question. It's kind of, it's where it's headed towards. So look at your diagrams very, very carefully. Okay, so that's our first one. Now we're going to get the force of T on P. So we're going to use the same formula. Okay, we've got K. This time we're going to use QP and we're going to use QT. So we've got 9 times 10 to the 9. Again, both of these charges are the same because this is after they touched, and all three charges have the same value after they touched. Now our distance is 0.3. And we get a value of 9 times 10 to the -7 newtons. And this one we said was to the left. So we got our directions even before we started the question, okay, from our free body diagram. Do you guys see that? So where do we go from now? We've got to get the resultants. So we're going to use Pythagoras. So the net force squared is going to equal the force of S squared plus the force of T squared. Okay. So our net force is going to be square root of 8.1 times 10 to the minus 6 squared plus 9 times 10 to the minus 7 squared, giving you 8.15 times 10 to the minus 6 newtons. We leave the direction off because they asked for the magnitude. Any questions?
No, ma'am.
Okay, cool. Okay, our next one then, I think they're asking us here for the field. So the net electric field, okay, at the origin, I think this is badly phrased. They should say at point P due to charges S and T. So we're looking for the net field at this point where we've calculated our net force. There's two ways of doing this. You can use the two field formulae and then add them together the same way we've done this. That's the long way around. Or you can use the net force to get the net field. So how do we do that? We say our net field is equal to the net force experienced per coulomb charge. Now here we are using small q. Small q is charge P. Because look here, they said that the field due to charge S and T. That means S is a big Q because it's the field of S, T is a big Q, and P is a small q. We've got two big Qs and one small q because we're looking at the combined fields of S and T, and P is experiencing that combined field. So S and T are responsible for the field, P is experiencing the field. That's why S and T get big Q and P gets small q. Right? So we're putting P's value in here. I know they are all the same, but we're putting P's value in here. Now our net forces is 8.15. So we've got 8.15 times 10 to the minus 6 divided by P's value. Now I'm going to leave this negative off so I don't overcomplicate things. 3 times 10 to the minus 9. Remember, you don't have to show the substitution of that negative, hey? If you do put that in and you get a negative answer, just make your answer positive. They've asked for the magnitude, so we're not putting in a direction. You would normally swap it out for a direction, but if they don't want the direction, just make the negative positive. Okay, that gives us 2.72 times 10 to the 3. What is our unit for field? Our unit comes from this formula. Let me just change my color here. Our unit comes from this formula. And I find out of all physical quantities, just what I've experienced, out of all physical quantities, the electric field is the unit that gets messed up the most. Go to your formula that defines the magnitude. That's this formula here. This formula defines the magnitude. It also gives you your unit. Your force is measured in Newton, your charge is measured in coulombs, and that gives you a unit of Newton per coulomb. Okay. Use your formula also to remember your units. Most of them work that way. Any questions here? Okay, cool. Our next one says, one of the charged spheres, P and T, experienced a very small increase in mass after it was charged initially. That gets missed. Initially, what happened in the beginning? Let's go back up here quickly. I went too far. Oh my goodness, this thing is so sensitive. So not my favorite program. Okay, yeah, initially. P, S, and T on insulated stands are initially neutral. Then they get charged by minus 15 times 10 to the minus 9 coulombs. and 2 times 10 to the minus 9 coulombs. So when they were initially charged, they they went for which sphere experienced an increase in mass? Okay, which one experienced an increase in mass? If they experience an increase in mass, it means they're gaining electrons. Remember, electrons are moving over. So if they're gaining electrons, they are negatively charged. So P is the one that gains the electrons and gains the mass. I know that electrons mass is like negligible, but it is there. Okay, it does have a value, even though it's like minuscule. So P is the one that gains the mass. Calculate the increase in mass experienced by P. Okay, so we're going to use the amount of charge, the minus 15 times 10 to the minus 9. That is the amount of charge it gained, which means we need to figure out how many electrons it gained from that charge. How do we do that? The number of electrons is equal to the charge gained divided by the charge on an electron. So the charge gained was minus 15 times 10 to the minus 9. And the charge on an electron is minus 1.6 times 10 to the minus 19. Now you can either make these two negative or you can make these two positive. It doesn't matter as long as your answer here is positive because they are number of electrons. So that gives you 9.38 times 10 to the 10 electrons. That's how many electrons it gained. They want the mass. Guys, the mass of an electron is a value on your formula sheet. So we take our number of electrons and times it by the mass per electron. So that is 9.11 times 10 to the minus 51, shows you how tiny this value is. And that gives you an overall mass of 8.55 times 10 to the minus 20 kilograms. Okay, tiny amount, but it's there and we can calculate it. Okay, Chris, so P is the one that gained the mass because P becomes negatively charged. So because P gained electrons to become negatively charged, it also gained mass along with those electrons. So if things lose electrons, they lose that tiny bit of mass. If they gain electrons, they gain that tiny bit of mass. Any questions, guys? Okay. Okay, so our question 3.2 says a small isolated sphere A with a mass of 0.2 grams carrying a charge of 7 times 10 to the minus 9 coulombs is suspended from a horizontal surface by a string of negligible mass. A second sphere B carrying a charge of minus 8 times 10 to the minus 9 coulombs on an isolated stand attracts sphere A so that the string forms an angle of 20 degrees to the vertical. The horizontal distance between the centers of the two spheres is 3 centimeters. Refer to the diagram below. Right, so B is attracting A. If you have a look there, B is a negative charge and A is a positive charge. So we will get an attraction force between A and B. Now A is hanging still. Okay, so if we draw a free body diagram of A, free body diagram is still the way to go. Actually, I think it is the question B. Okay, so draw a vector diagram or a free body diagram of sphere A. So if we look at sphere A, it's being attracted towards B. So that's going to give you your electrostatic force. It has got a tension in the rope upwards in that direction. And then it has a weight downwards. Oh, my arrows are so skew. Okay. You can take this and shift it into a triangle, or you can put components for T. So you can either put, so if we look at our components here for T, you've got a TX and a TY. Okay, or you can shift the three forces into a triangle. Whichever method, it's the same thing. Okay, this is your angle that's 20 degrees. Now, our electrostatic force balances the horizontal component of our tension, because remember A is stationary, and stationary means everything up balances everything down, everything left balances everything right. Okay, so the electrostatic force balances that component of T, and our weight balances the vertical components of T. So all our forces are balanced, and that's why it is stationary. Now just check, guys. I hope I didn't look wrong, but it looks like there's a lot of angle mix-ups in your notes, so in the memo. So I'm going to go through the answers and just check. So as where I looked at it, option 2 in your memo looked like it had an error, but let's have a look at the next question. Calculate the magnitude of the electrostatic force, highlight that word, that sphere B exerts on sphere A. The focus here is on A. So let's just think about that force quickly. The force is the same on each sphere because it's a Newton third law force pair. So A experiences the same force as B, but they experience that force in 2 different directions. Now, if they just said calculate the force between A and B, your answer would have a direction of attraction because they attract each other. But this question is focusing on A, and A experiences a force to the right because of B. Okay, so the direction here is to the right. It's not attraction, it's to the right because we're focusing on A. If they asked us for the force on B, we would say B experiences a force to the left. But if they ask for the force between the 2 charges, it's just attraction, because then they're not specifying which one. So read your question carefully. They also say the magnitude, so we don't have to put that direction in either. Okay, so the force. Force is F, so we've got F is equal to K, Q over R squared. And this is 9 times 10 to the 9. Our sphere A is 7 times 10 to the minus 9. And B is minus 8 times 10 to the minus 9. I'm going to leave that minus off. So 8 times 10 to the minus 9. And our distance is 3 centimeters. That gives us 0.03 meters. Remember to do that conversion. And that's going to give you a force of 5.6 times 10 to the negative 4 newtons. They just want magnitude, so we're just going to leave it like that. We're not going to put a direction. Okay. So this would be the same as option A in your memo, or option 1. Option 2 in your memo uses the weight of the object and then gets the component X, which would work, but there is an error in option 2. It says tan of 70 where it should say tan of 20. Okay, so there is an error there, I think. Latable, so the diagram, I drew a free body diagram. Okay, the one with the dot. The vector diagram uses a block, but vector diagrams aren't really in the syllabus anymore. So this is an old question. So it would just be a free body diagram. A vector diagram is the exact same thing, except without drawing a dot, you just draw a block to represent your charge, or a circle to represent your charge, and then you draw the forces on it like that. So it's pretty much the same thing. I just do the free body diagram because those are the ones that we do nowadays. Okay, now the next one says calculate the tension force in the string. So we're looking for T. Okay, so we know that our electrostatic force balances the X components of T. So we can use our sine component, I think is the easiest one, which is not an option on your memo. We can use that sine component to calculate that. I'm just going to move this up a little bit. Okay, if you look at this triangle over here, so your tension triangle, your Tx is equal to the electrostatic force. So Tx equals Fe because the whole thing is balanced. So if you go Tx over T, in other words, opposite over hypotenuse, I'm working from the 20-degree angle. Opposite over hypotenuse, that is sine of 20. So this is the value 5.6 times 10 to the minus 4. That's what we just calculated. over tension equals sine 20. Now be very careful here when you manipulate this. Because we're looking for the hypotenuse, we're going to end up dividing by sine 20. So we're going to go 5.6 times 10 to the minus 4 divided by sine 20 equals the tension. So the tension is then equal to 1.64 times 10 to the minus 3 newtons. Okay, so the correct option in your memorandum would be option number 3. That one works. They've worked from the 70-degree angle. They've worked from that one over there, and then they've used the weight instead. I think. No, they use the x of the component, but they use the cos. Sorry, they use cos of 70, which is fine. That gives you the same answer. Okay, so that's what they've done in your option 3. Option number 1 and option number 2, I don't think are correct. I think there's errors. Okay, any questions here, guys? Nope. Okay. Let's go on to the next one. Question number 3.3. So 3.3, I'm skipping all the definitions, hey? Okay. The diagram below shows Q1 with a charge of 4 times 10 to the minus 6, that's micro. So 4 microcoulombs, placed 10 centimeters from a charge Q2 with a charge of 5 microcoulombs. The net electrostatic force exerted on an electron placed at point X is 0 newtons. Calculate the distance in centimeters between Q1 and point X. This is a very particular question. Okay, now I want to say something about this question. Where you've got this little net force of 0. Look at the mark allocation here, it's 5 marks. The maths in this question is big. But 4 of those 5 marks all lie in the equating the two equations and substituting your values. The answer is worth 1 mark. So if you don't know how to go further, leave it alone and move on with your paper. I'm going to show you how to get there nice and easily. But this question is not worth fighting for the answer. If you equate the two equations and substitute in your values, you've got 4 out of 5 marks already. It's not worth spending 10 minutes sifting through maths to get to your answer, because we don't credit the maths, we credit the science. And the science is all in the first couple of steps. So what's happening here? Because this is let's see, we've got 2 positive charges here. So there's a field in that direction, and then there's a field in this direction. So the fields are opposite, and they're saying that at point X, these 2 fields balance each other to give a net of 0. So there is 0 field at X. So if you put an electron at point X, it also experiences 0 force. Think about that. If there is no field at point X, there is no force experienced at point X. So the 2 fields are equal to each other at that point, or the 2 forces experienced by the electron are equal at that point. So if we look at the formula for the forces, you can use the forces or the fields, it really doesn't matter. So let's say the force of Q1, is going to be K Q1, the charge on the electron, and R squared. Okay, so let's make this distance from Q to X. Let's make this distance here. Let's make that R. Got it? Now, the force of Q2 to the electron is K Q. So this was Q1. This is Q2 times the charge on the electron. Now, our distance here is the 10 centimeters minus R. 10 centimeters. So what's 10 centimeters? 0.1. Okay, minus R, and that is squared. Do you see what we've done with the distances? If this distance is R, then this distance is the 10 centimeters minus R for the remaining distance. Okay, now the 2 forces are equal to each other. Yes.
Ma'am, why is there the small q?
Oh, that's the charge on the electron. So they tell us that, and where did they say? Yeah, an electron is placed at point X. So they're actually going to put a little electron there. So small q is the charge on the electron.
Thank you, ma'am.
Okay, cool. Now, guys, so these two forces are equal to each other. So we're going to say K Q1 times the charge on the electron over R squared is equal to K Q2 times the charge on the electron over 0.1 minus R, and that is squared. Okay. Equating the two formulae together gives you your first mark. Now, substituting in gives you your second mark. But before you substitute in, just notice what cancels out. Your K cancels out with K, and the charge on the electrons cancel out as well. So you don't have to substitute that in. If you substitute in as little as possible, it makes it easier. Otherwise, it just becomes lots of figures, lots of numbers, and it just becomes overwhelming. So we can put charge Q1 in here. Now, check your memo. I think the question was changed at some point, and the memo's values didn't change with it. Q1 is 4 microcoulombs. So we're going to put that in, 4 times 10 to the minus 6. And then we're going to leave that over R squared. Then Q2 is 5 microcoulombs. So 5 times 10 to the minus 6. And we're going to put that over 0.1 minus R squared. Okay, guys, at this point, you have 4 out of 5 marks. If you don't know how to solve for R, leave it. It is not worth the time you're going to spend fiddling with it. Okay. Now, to calculate R, to solve for R, the last thing you want to do is times in that square into that bracket. Don't do that. Let me show you how to get there nice and easily. We're going to maneuver these so that we get our R's on the one side and our numbers on the other side. Okay, so I'm going to times by the 0.1 minus R brackets squared on both sides so that I get 0.1 minus R squared here over R squared, and I'm going to divide by the 4 microcoulombs on either side. Okay, so now do you see what I've done? I've just put my same variables on the same side. And I've got the two roots on the same side. So if I square root both of these, then my squares go away. I don't want to times that into the brackets, okay? I want them to go away. Just also check these times 10 to the minus 6s, those cancel out as well. So your numbers very quickly becoming nice and small. So if I square root both of these, I get 0.1 minus R over R is equal to 1.12. So I can times that R away, and I get 0.1 minus R is equal to 1.12 R. Take that negative R over to the other side and add it, so that 0.1 is equal to 2.12 R. And then solve for R. So R is equal to 4.7 centimeters. Wait, let me undo. First 1 centimeters. Space. Okay, let's first put it in meters. So our meters is 0. It's going to give us 0.047 meters. They didn't say centimeters, but it would equal then 4.7 centimeters. Okay. Do you see how much maths lies between your 4 marks and your last mark? Okay, you don't get credited for that maths at all. If you get the last mark, great. You get one. If you get the answer, you get that last mark. Okay, but it is not worth 5 minutes of your time. So if you're not going to get there in a minute, it's not worth it. Okay, the negative R, I moved to the other side of the equal sign, so I added it on the other side. So my 1.12 became 2.12. I added it. Okay, cool. Sorry, I do tend to lose people on the math because I tend to skip math steps. It's very bad. I'm not a math teacher. Guys, are there any questions on this? It's a very sort of standard 5-mark question, okay? But if you can do that top part, 4 marks, it's good enough, move on, all right? If you feel like this is maths that you don't feel like sitting on, or if you tend to run out of time, if you're one of those people who generally struggles with time and you get something like this, remember, put your values, substitute in, and move on to the next question. It really is not worth your time for that 1 mark. Okay. Our next one says, oh, just check this one also in the memo, hey, because the memo used different charge values. So the memo's answer is slightly different because I think it came from, I think the question was changed at some point. Okay, so now our next one says M is a positive point charge. Sketch the electric field pattern caused by M. Okay, so basically you're just looking at a positive charge and the field pattern around a positive charge. Space your lines out nice and evenly, make them all nice and straight. They must sort of move away perpendicular to the charge and make those arrows point outwards. I see this quite often, and I don't know where this comes from, but people like curl it all the way around the thing. Your field lines are going to curl unless it's influenced by another charge. But if it's on its own, they're straight lines. Okay, so don't do that. Our next one, so we've got P and T are 2 points, some distance to the right of M. The distance between P and T is 3 millimeters. The magnitudes of the electric field at P and T is 3 times 10 to the 6 Newton per Coulomb and 5.5 times 10 to the 5 Newton per Coulomb, respectively. So they've given us 2 scenarios. If you get given 2 scenarios, your mind must already start going, was probably simultaneous equation. Okay, if you've got 2 scenarios, you're looking at simultaneous equation. Define in words the term electric field at a point. So this one is the, if you're looking at the magnitude of the electric field at a point, it is the force experienced per unit positive charge. They just say describe an electric field, then you look saying that it is a force, a region in space where a charge experiences a force. Okay. Okay, now here again, I think the charge values used on the memo were different. So I think the same thing happened with this question. Okay, the charge values are slightly different. So I'm going to give you the correct values, I hope. And please just double check my math here. Hey? Let me know if I've made any mistakes. So what we're doing, we've got 2 scenarios. For each field, we've got K, Q, and Q. This is Q of M, the charge of M. We're working out M's field and the distance squared. Okay, so let's see. For P, if this is the field at P, the field at P is 3 times 10 to the 6 Newton per Coulomb. So 3 times 10 to the 6 Newton per Coulomb. We've got K. We're looking for QM. And I'm going to make that distance R. So the distance from there to there as distance R. Okay, we've got K. We don't have Q. We've got Q is basically a variable and R is a variable. Okay, we do have K. But I'm going to leave it there. Let's do our other one. The field at T, same thing, QM. And our distance now is R plus 3 millimeters, 0.003. Okay, so the value for the field here is 5 times, 5.5, 5.5 times 10 to the 5 K QM over R plus our 3 millimeters squared. So we've got 2 formulae, we've got 2 variables. Okay, so it is a simultaneous equation. KQM is similar in both. So I'm going to get KQM for this one. So KQM here is equal to 3 times 10 to the 6 times R squared. And KQM here is equal to 5.5 times 10 to the 5 times R plus 0.003 squared. Okay, as far as possible, don't times in that square. Now, Okay, QM is the same for both. So we're going to equate these. We're going to go 3 times 10 to the 6 r squared is equal to 5.5 times 10 to the 5 times r plus 0.003 squared. And we're going to do the same thing that we did now. Okay, we're going to square root these squares away instead of timesing them in. So I'm going to divide my r squared down to the bottom, and I'm going to divide my 5.5 to the bottom. So I've got 3 times 10 to the 6. You know what I'm going to do here? I've got a times 10 to the 6, and I've got a times 10 to the 5. So I'm going to put them both times 10 to the 5. So 3 times 10 to the 6 is the same as 30 times 10 to the 5. Agreed? Okay. And put that over 5.5 times 10 to the 5, because now my times 10 to the 5s cancel out. And then I've got r plus 0.003 squared over r squared. Okay, so look at the maths. So I'll put my two variables, same variables or terms on the same side. Okay, I've got my r's on the one side, my numbers on the other side. I'm going to square root both sides so I can get rid of those squares. Okay. Now, after I've square rooted this, it's going to give me 2.33. And this is going to give me r plus 0.003. Do you see how nicely those squares just disappear? So, okay. Now I'm going to times my r over. So I've got 2.33r equals r plus 0.003. Throw my r over, so I'm going to minus it from that side. So I'm going to have 1.33r equals 0.003, and our solve for r is equal to 0.002 meters. Fantastic. I don't have the answer yet. So this one, unfortunately, you do have to go all the way down because we're looking for Q. We're not looking for the distance, we're looking for Q. Right? But I'm going to sub this back. So I'm going to take my formula, which one? I'm going to take this one up at the top here, that one. I'm going to use that one to get my Q. So I'm going to sub in. So I've got 3 times 10 to the 6 equals 9 times 10 to the 9 times my Q of M over, now I've got the distance is 0.002 squared, and then I solve for Q, and I get Q equal to 1.68 times 10 to the minus 9 coulombs. Times 10 to the minus 9 is nanocoulombs. You don't have to put it in nanocoulombs, but it's good to practice. That is the whole thing. All right, so please note that the solution is the same in your memo. It's just that they've used different charge values for some reason. So the charged values don't match the question. Any questions, guys? Okay.
No.
No, got it. Very mathsy, hey? Very mathsy. So this one, because now you have to substitute that r back into your equation. If you don't solve for r, you'll lose 2 marks for the red parts as well. Still not worth spending 10 minutes on. You've got to manage your time. Managing time is actually even more important. Okay. Guys, if you get to something like this, or like a carryover error type question, where you need an answer to work something else out, and without that answer, you kind of get stuck, give yourself an answer to use. So let's say, I'm going to do this in blue. Like, let's say you get to this first part, okay, and maybe you equate your two equations to each other, and you don't know how to go further, or you're struggling, or the maths is just like blown up, and you don't even know how to get your way out of that. Just ignore everything and give yourself an answer. So let's say r is equal to 0.001. It doesn't matter. Just give yourself an answer to use, because then at least you can get some method marks. You still won't get the final answer mark, but you can get some method marks for substituting that value back in. Okay, if it's carry over from one question to the next question, you will still get full marks for that next question, even if you've got absolutely no idea how to do the previous question. And they say, calculate the charge here, and you don't even know where to start. Just say, charge is equal to, and make something up, 2 coulombs. And then use 2 coulombs in the next question. You'll get full marks for carryover error, instead of leaving the second one out as well. Okay, so just put in a value in the previous question. You'll get 0 for that one, but at least you'll get the next one, because you'll get full carryover error.
Ma'am,
Yes.
where does the R come from on the second one? R.
On the value R. So
Yes.
I
Oh,
said
okay,
at the
okay,
top
yes,
here.
ma'am.
Got it. Okay.
Okay, thank you, ma'am.
All right. Pleasure. Okay. Guys, let's go on to the next one. We've got 2 more questions left. So 3.4. 2 metal spheres, Q1 and Q2, on insulated stands carry charges of 6 microcoulombs and minus 4 microcoulombs, respectively, and are separated by a distance of 3 meters from their centers. A point charge at P is 1.2 meters from Q2 in the same plane as indicated in the diagram below. So our P is sitting here towards the right. Okay, we've got another definition of Coulomb's law. I'm going to ignore that one. Draw an electric field pattern between the 2 charges. Now let's see, they are, one's positive, one's negative. So we've got a positive charge and we've got a negative charge. They are going to give us an attractive force in the middle, which means we're going to have this net field in the middle. Okay, so it's going to give us that pattern. Don't let your lines touch. And now Q1 is 6, Q2 is minus 4. 6 is greater than 4. Forget about the positive and the negative. 6 is greater than 4, which means that we need more lines around here. So I'm going to try and put more lines here. Okay, make that one touch. And I'm going to try and put fewer lines here, so that it's obvious. Okay, and now it's going from positive to negative, so away from positive, and towards negative. What's this one doing? Okay, something like that. Practice those. Don't just go, oh, that's easy, I can do that, I don't need to practice it. Practice it. Our next one says, calculate the electrostatic force exerted by Q1 on Q2. If it said between them, we would have said attractive force, but it's by Q1 on Q2, which means that we're focusing on Q2. That's our focus point. Also, force. Highlight the word force. Force is F. Field is E. Okay, let's have a look what's going on here with Q2. Q2, is going to be attracted towards Q1. So it's going to be experiencing a force towards the left. So your direction is towards the left. Please check that. The memo says right. It's not towards the right. It's towards the left. Q1 experiences a force towards the right. But the question is asking the force on Q2. So our focus is on Q2. Okay. Oh, we need the values. So we've got force is equal to K Q1 Q2 over R squared. K is 9 times 10 to the 9. Q1 is 6 times 10 to the minus 6. Q2 is 4 times 10 to the minus 6. I'm going to ignore that negative and not substitute in that negative. So 4 times 10 to the minus 6. Because we've already reasoned our direction. Okay, we don't need the negative. We've reasoned our direction already. Our distance is 3 meters, and don't forget to square it. And that gives us 2.4 times 10 to the minus 2 newtons left. They didn't say magnitude, so you do need a direction. Okay. The next question says calculate the electric field strength. Okay, highlight. Field. Field is E. Force is F. Field is E. The electric field strength at point P as a result of Q1 and Q2. So this is not, we just calculated the force between those two charges. We're now looking at a field at point P. Okay, so we've got to calculate the field of Q1 and the field of Q2 at that position, and then see if we must add them or subtract them. Now, let's have a look at that quickly first, before we calculate these fields. First of all, because we're calculating the field of both of them are big Q. We're calculating each one's field. There is no small q. There'll only be small q if we put a charge at position P, then that one would be a small q. But Q1 and Q2 are both big Qs. Now, Q1 is positive, which means its field is outwards. Okay, so if we're looking from P's perspective, the field is to the right. So we've got a field of Q1 to the right. Q2 is a negative charge, so the field comes in. Okay, if we're looking from point P, the field is to the left. So there's a field of Q2 to the left. So just by looking at that, you can already see you're going to subtract these two fields from each other, because at point P, the two fields are in the opposite direction. You're looking at that arrow and you're looking at that arrow. Because you're looking from point P, you're looking at the charge. Okay, so let's do this calculation quickly. And let's do this one green. Okay, so our two fields. The field of E1, we're going to use the one with distance because there is no charge at point P, so there is no force. We've got the distance away from Q1. So we've got K, Q1 over R squared. K is 9 times 10 to the 9. Q1 is 6. This was the 6, hey? Yes. 6 times 10 to the, what was it? I'm having to go back, -6. They were micros. Now the distance, look here quickly. The distance, you're going from Q1 all the way to P. So it's the 3 meters plus the 1.2 meters. You've got to take both distances there. So 4.2 meters. And square it. That's going to give you 3061.22 Newton per Coulomb. And that one was to the right. Happy with that, guys? Okay. Then the other one. So the field of 2, we've also got K. Now we're going to use Q2. So K is 9 times 10 to the 9. Q2 is 4 times 10 to the -6. And our distance is now only the 1.2. Okay, and that's going to give you 25000 Newton per Coulomb to the left. So once to the right, once to the left, we're going to subtract 2 from each other in the bigger one's direction. So 25000 minus 3061.22, and this is E net, eh? And that's going to give you 2.19 times 10 to the 4 Newton, oh, that's a 4, Newton per Coulomb left in the bigger one's direction. Okay, please check, guys. Make
Sorry,
sure that
ma'am.
you understand. Yeah,
How would you do it as one big equation?
you can't do it as one.
So you
You
don't
can't-
do 2 separate ones.
You have to do 2 separate ones. Yeah. Yeah,
Okay, thank you.
pleasure. Okay. All right, guys, you happy with that?
Ma'am,
Yes.
Just to like verify, I wouldn't lose marks if I said E1 minus E2, right?
No, no, you wouldn't lose
Okay.
marks. What would happen is your answer would first be negative, and then you would just interpret that as to the left. So you would just make your negative positive and add to the left. Okay. Awesome, guys. All right, let's carry on. You're doing well, hey? We're actually flying through these questions. You guys are doing really well. How many electrons are in excess in Q2? Now, Q2 has a charge of -4 times 10 to the -6 coulombs. So if you want to know how many electrons, you need to divide that by the charge on an electron. So let's do that quickly. So we've got the number of electrons is equal to the charge divided by the charge on an electron. The total charge was 4 times 10 to the -6. Now you can make that negative if you want, but then you must make your charge on an electron negative as well, as long as both are negative or both are positive, so that you can get a positive answer. And that gives you 2.5 times 10 to the 13 electrons. Okay, so if they ever say how many electrons, you're always going to divide by the charge on an electron. All right, guys, we've got 10 minutes left and one more question. I think we can do it. Okay, question number 3.5. Point P is 5 centimeters from a sphere with a charge Q as shown in the diagram below. Now, point P is a position. It's just a space. There is a field at that space because that space is close to charge Q. There is no force there because there is no charge in that space. But if we had to put a charge at position P, then there would be a force there as well. Okay, so a field will exist even if there is no force. The field is there just because it's close to a charge. The electric field point P is E to the left. So the field size is E and it's to the left. So in other words, the field is going in that direction. Okay. Define the term electric field. We're going to skip the definitions. Draw the electric field pattern around the charged sphere. So if at point P it is to the left, it means that this is a negative charge. The field is coming inwards and the field pattern is going to be something like that. Oh, these lines are not perpendicular to the surface and they're not spaced out nicely. Okay, but that's your field pattern. So you're looking at the inwards field. It's coming inwards. Okay. A charge of -4 times 10 to the -9 coulombs is added to the charged sphere. The magnitude of the electric field point P is now 3E. What's happening here? You've got two scenarios. With the charge Q, the field is E. So let's see, with the charge Q, the field is E. With the charge Q plus 4 times 10 to the 9, the field is 3E. So again, a simultaneous equation, or this could be a manipulation of formula type question. All right, there's two scenarios here. The first question says calculate the number of electrons added on the sphere. Okay, so that's quite nice. We've got the charge added on the sphere. So the number of electrons is just going to be our charge divided by the charge on an electron. So we've got 4 times 10 to the 9 divided by 1.6 times 10 to the -19. Sorry, this is a -9. And that's going to give us 2.5 times 10 to the 10 electrons. Okay, so that one's a nice and easy one. Now the next one says calculate the magnitude of the initial charge Q on the sphere. All right, let's have a look here. We've got to take our two scenarios into consideration now. So when the field was E, we've still got K, the charge was Q, and the distance stays the same, so R squared. Okay. After the change, the field is now 3E, K stays the same, but our charge is now the original charge Q, our original charge Q plus the extra charge of 4 times 10 to the minus 19. Okay, that was added to the sphere. The same distance. They didn't change distance. All they did was add to the charge. Right? So now we're going to sub in. I'm going to take this part here for E, and I'm going to put it into E's spot there. So we've got 3 times KQ over R, over R squared is equal to K Q plus
ma'am.
4. Yes.
Ma'am, how did you get the charge as 4 times 10 to the power of negative 19?
Oh, what did I do? Hang on, I think I might have written something stupid down. Negative 9, sorry. And it's negative charge, eh?
Yes, ma'am, it's negative.
It's negative charge. Wait, let me just read that again. The charge of that is added to the sphere. Okay. So we've got to add a negative charge. Then just check the memo for me again here. All right. So 19 is a dumb mistake. It's negative 9. And then let's just check the memo. All right. So that we're adding the negative charge. Okay. So basically that positive becomes a negative. Yes. That's right, hey?
Yes, ma'am, it is.
Yes. Okay, good. All right. So let's make this positive and negative here. Here we go. Thank you so much for spotting that. Okay, times 10 to the negative 9. There we go. I'm going to have to work out this little thing on the memo. All right, so now we're solving basically for, well, ultimately we're looking for Q, but let's see what cancels out. Okay, so K cancels out with K and R squared cancels out with R squared, leaving us with 3Q is equal to Q minus 4 times 10 to the minus 9. Okay, and now we're just solving for Q. So Q is equal to, now we need to check this memo because they've got a positive there. So let's see, 3Q minus another Q gives us 2Q is equal to negative 4 times 10 to the minus 9. So if we divide that 2 away, oh, I think it is right. It's just going to be negative. Is that right? Guys, are you in agreement with that?
Yes, ma'am.
Awesome. Awesome. Okay, a lot of the stuff cancels. So before you sub in, check what cancels first, because you don't want to be overloaded with a lot of numbers. That's not fun. Okay, so check what cancels, then substitute in your values. Okay. The table, you want me to repeat B. What is B? B. Oh, the electric field around the charged sphere, that one. Okay, cool. So that one comes from over here. It says the electric field at P is to the left. So if you're looking from P's perspective, the field is pointing to the left, which means the field is going inwards. And if it's going inwards, it gives us a negative charge. And that's how we know what, so we're basically drawing the field pattern around a negative charge. But that's what tells us that it's a negative charge. Make sense? Cool, awesome. Actually, this answer also makes more sense now because it's a negative answer. The memo had a positive answer. So thanks for spotting that error. That makes this one, it clears this one up as well.